Hello and welcome to Physics 1401. Today's topic is acceleration and Newton's second law. Now please watch the video called Vectors Part 1 if you haven't done so, because most of the topics which will be covered here are based on that, and actually many of the definitions are already made in that video. So I suggest watch that video. Here's the address. I'm just gonna copy this under description, but here's the address, and I'm not gonna go over everything which is already covered in those videos. So okay, so please watch that video. It's called Vectors Part 1. Vectors Part 1. So what is in that video? The definition of position vector, displacement vector, velocity vector, average velocity, and instantaneous velocity. A vector subtraction of position vectors, and acceleration vector. Okay, so if I just summarize what's in that video, which you should watch, is number one, the definition of a position vector. Position vector, which is called R. Okay, so R tells you where you are in the three-dimensional, it could be two-dimensional too, plane. Let's say these are the XYZ coordinates, and let this represent the motion of any object in that three-dimensional space. Basically, you consider a vector from the origin, and this vector will point at where the object is at a given time. Okay, so that's the R vector, the position vector. And then using the position vector at two different times, you can come up with a displacement vector. For instance, this is at t equals some time, t initial. At a later time, the object is here, let's say. This is t final. And then let me use a different color now. I can use a vector like this. This will be the new position vector. The old one was Ri, and now Rf, F meaning final, right? So it just follows you around. And then you subtract these two vectors and get the displacement vector. So we also have displacement. These are explained in detail in that video. I'm just going fast. Just a very quick review. Displacement, which is delta. Delta means difference. Delta R, that is the final minus initial. So that would be a vector like this. Okay, delta R. If you remember the vector addition rule, the tail to tip, this means Ri plus delta R is Rf, which is nothing but the definition of delta R, right? If you subtract Ri from both sides, that's what you get. That's displacement. So position and displacement are not the same, okay? Please watch that video. These are explained in detail. Now in this video, I'm going to focus on only one dimension. I'm going to assume that it's a one-dimensional motion, so let's say I'm going to pick x and get rid of y and z without loss of generality, really, because I want to focus on solving problems, actually. So what if you look at this motion at smaller time intervals, okay? That will actually get you to the idea of instantaneous changes, right, which are small changes, not as big as delta R here. Well, delta R can be used to define the average velocity, delta r over delta t would be the average velocity. But what happens when delta t goes to a very tiny increment in time? We call it the limit, right? Limit when delta t goes to 0. Well, that gives you the instantaneous velocity of the object. Okay? So in that video I talked about this also, and then showed that this vector actually can be found on that picture here. So let's use red again. For instance, right here, when the object was there, you can now think about it. It's moving like this, like that, right? It's making a turn over there. But right at this instant here, it will have a velocity vector which will point in the direction of a tangent to the curve, like this. Okay, so this will be the instantaneous velocity. But the average velocity is just in the direction of delta r due to this relationship here. Okay, so delta r and the average velocity are always parallel. But to find the instantaneous velocity, you're going to draw a tangent line to the curve that represents the motion of the particle at that instant. Okay, along that tangent, you will find your instantaneous velocity vector. And if that vector changes direction, as it does in this case also, you have a change in the velocity, therefore acceleration. Okay, so I'm just giving a quick review here. Please watch the video to see that in detail. So the change in velocity means delta v, right? V final minus v initial. If you divide it by the change in time, delta t, that gives you the average acceleration. And what happens if you do the same limit process? Look at the motion within smaller and smaller time intervals. That means delta t goes to 0. Then this becomes the instantaneous acceleration. Simply a. Okay? And a does not have to point in the same direction as velocity. It may or it may not. If they're parallel, it may mean speeding up. But what if you're slowing down? Then the velocity vector and the acceleration vector are in the opposite directions. In one-dimensional motion, either parallel or opposite, but in two-dimensional or three-dimensional motion, they do not even have to be parallel. I mean, they can have an angle between them. But that's kind of advanced for today, so let's leave that for some other time, okay? But pretty much that's what was covered in that lecture video. Please watch that. Make sure these definitions make sense to you. And then what is not in those videos is, I think, how to find the change in position given some velocity, okay? Or given the acceleration, how do you find the change in the velocity? Okay, so let's remind ourselves how to find the velocity from a position time graph. Now I'm just going to focus on one-dimensional motion. So x is my position variable, but I'm going to plot it as a function of time. Okay, this is time. Now I cannot have those funky pictures because I cannot go back in time, for instance, so these things are not allowed, right? I can only have things like this maybe. For every time point, there can be only one x, for instance. You cannot go back in time, you cannot occupy two different locations at the same time, things like that. But this graph, for instance, represents moving along the positive x direction in time as time passes, okay? So given this, how do you find the instantaneous velocity, for instance? To do that, you look at the the slope of the tangent to this curve at that point. I think that video covers these already, so you can just review that. So you just draw a tangent to that curve, and the slope of this will give you the instantaneous velocity. Okay, so we know how to go from position to velocity. You just check the slope at every point you can find, and then that'll give you a picture of the velocity. Like in this case, if I plot velocity, let's see, when t is 0, I have a slope like this. Okay, maybe over here, but later that slope increases. Okay, at a later time I need a larger velocity, and then the slope gets less again. So this could be something like this. Okay, not exact, but it could be. Why not? Right? Basically, you reach your maximum velocity somewhere around here when you have the largest slope. Right? So that's also in the video. But what's not in that video is how you go from a given velocity time graph to position. Okay, actually what you can really calculate is the change in the position, the displacement. Okay, given a velocity graph only, you will never know what your x will be at a given time. Okay, you can always find delta x, but not just one x. What you do is really simple. You consider the area under the curve here. This will give you the change in x, the displacement. Okay? And if you know what your initial x was, you can calculate your final x. That's fine. But this method of finding areas under velocity time curves will not give you by itself xf or x initial. It's going to only give you delta x, which is x final minus x initial. Okay, so same thing applies to the relationship between velocity and acceleration. You consider the slope of the velocity time graph. That gives you the instantaneous acceleration. But given the acceleration time graph, to go to the velocity, you have to find the area, and that's going to give you the change in the velocity. So if this is your acceleration, some arbitrary function, but it has to be a function of time, okay? A is a function of time. What do? You find the area under it. This will give you the change. Delta means change in V. So V final minus V initial. You calculate the area. If you know one of the two velocities on the right hand side, you can find the other one. But if you don't know them, basically you have two unknowns, you can only find the difference between them. Okay? You don't know the initial velocities. You don't know the individual velocities. So this was what was missing in that video. And the main topic today is Newton's second law. Once that we have this concept of acceleration, which has to do with the change in velocity, now we think, okay, why do we have acceleration, or why does velocity change in the first place? If you go back to Newton's first law, if the net force on an object is 0, the object will have a constant velocity. For instance, move along a straight line with constant speed, right? Speaking of speed, by the way, make sure when you watch that video you understand the difference between speed and velocity, okay? Especially the difference between average speed and average velocity, all right? In the case of instantaneous speed and instantaneous velocity, you know, it's not too hard really. I mean, you just basically take your instantaneous velocity and find its magnitude, and that is the instantaneous speed, always a positive number, right? In the case of average speed, you have to be really careful because, for instance, average velocity can be 0. Okay, you start at a point, let's say you want to go to HEB for groceries. Okay, you leave your home, go there and come back. Okay, your change in the location is 0. Displacement is 0. Therefore, average velocity is 0. But you knew that, your average speed was not 0, and your speedometer in your car showed a positive number, right? So there is subtlety there. Make sure that's going to actually come again in the other chapter, chapter 4. But just keep in mind, there's a subtlety there that has to do with the difference between average speed and average velocity. So, and the object, if the net force on the object is 0, it's going to continue moving along a straight line with constant speed. Yeah, but what if the force is not 0? Okay, you add all the forces acting on the object in a vector fashion, and then you have a non-zero net force. Then what will happen? Okay, that's what the Newton's second law does. It tells you how it will accelerate. So a non-zero net force means there will be a change in the velocity, and every time you have a change in the velocity, there's acceleration, okay? And that's because of a force. Now, speed may not change, but velocity may change, okay? If you're going along a circle, all right, on the highway, you're making a left or right turn, your car's speedometer says 35 miles per hour. Your speed is not changing, but your direction is changing. And since velocity is a vector, right, its direction is changing, that does count as a change. So there is acceleration there, okay? Your speed is not changing, but you are still accelerating because the direction of the velocity is changing. And that's because there is a force on your car, okay? Or Earth going around the sun, okay? Now that speed also changes a little bit, but assume it did not change, okay? It's an approximation. Even in that case, the velocity is constantly changing. Why? Because there's a force acting on the Earth, and that force is the gravitational pull of the sun, right? So, that's what Newton's second law is about. Whenever there is a change in the velocity, therefore acceleration, there is a force, or vice versa. And these two are proportional, meaning if I increase the force I'm exerting on an object, if I increase that force, acceleration will also increase in a linear fashion, meaning if I double the force, acceleration will double as well. This can be checked experimentally, okay? Or if I divide the force by 2, acceleration will be half of its original value. What if I don't change the force, but I change the object I'm pushing, let's say, okay? Let's say I take the engine from a sports car, which can go up to 60 miles per hour in a couple of seconds, and I install that engine to a van or a heavy truck, an 18-wheeler, okay? Assume I can do that. Well, you don't expect that heavy truck to accelerate the same way, right? Because the mass increased. Mass. Now, we already saw the idea of mass in the previous chapter in the context of the gravitation, like the gravitational pull between two objects, right? The formula went like F equals the universal gravitational constant times m1 times m2 divided by r squared. You remember this formula, right? So you already know what mass is in a way. This is the gravitational mass, like weight was m times g. That's called gravitational mass. Now, when you think about the motion of objects, like acceleration, we call it the inertial mass, because mass will be a measure of how difficult, or easy for that matter, to accelerate an object. Like you take that engine from the sports car and plug it into heavy truck, but the truck will not accelerate that fast. So what changed? Okay? The mass changed, but the acceleration is inversely proportional to mass. Heavier the object, harder it is to accelerate the object. Okay? So force is linearly proportional to the acceleration, but mass is inversely proportional to the acceleration. So if you put those together, you arrive at this simple equation. The net force on the object will be equal to its mass times its acceleration. And you can write it as a vector actually. So F net is by definition the vector sum of all forces acting on the object. This sigma in mathematics means addition, right? So you add all the forces from 1 to n. You add them up. Okay, this means F1 plus F2. So I changes. The index takes values from 1 to all the way up to n. N is a large number, or the number of forces you have. You add them up, you get the net force. Okay, the net force will be equal to the mass times the acceleration. So you can rewrite it in terms of as a solution of A, if you like. So A will be equal to 1 over m times the net force, right? So it's obvious that if you increase the mass, keeping the force the same, acceleration will be less, or vice versa. There's an inverse proportionality there. Okay? So m is the proportionality constant between force and acceleration. It tells you how difficult it is to accelerate the object. Alright, so this is the inertial mass. Inertial mass. There's no gravity here, right? It's just it has to do with the motion, concepts of motion, inertial mass. Whereas this was gravitational mass. But we don't have different masses. We just have one mass, right? The objects have one mass, so these two are equal, okay? And many experiments have been performed over the last century. I mean, nobody could find any evidence that these two should be different, okay? The gravitational mass is equal to inertial mass, theoretically and practically. Okay, so that's Newton's second law. So we have three laws, and the first and the third laws were discussed in the previous video. This is the second law, F equals ma. And many problems can be solved using this simple law. You just have to draw a free body diagram, show all the forces acting on the object, and then based on that free body diagram, write down your F equals ma. It is a vector equation, so write it in terms of components, meaning if this is a 3D problem, f net x will be equal to m times x component of a, and then you can repeat the equation for y as well. F net y will be equal to m times ay, and then f net z is equal to mass times az. Right? It is actually three equations. Some problems in the book, like the inclined plane problem, I saw that in the chapter here. It's a two-dimensional problem. You don't have to worry about z. So x and y can be enough. And many problems, like free fall, is simply a one-dimensional problem. Okay, so draw your free body diagram, and then write down your equations of motion, which is nothing but F equals ma in those coordinate systems. And then once you have your equations, what is left to do? Just solve them, okay? Solve them for the unknown, whatever is asked from you for that problem. That's step number 3. Step number 1, free body diagram. Step number 2, F equals ma. Step 3, solving the equations, okay? This applies to many problems. And if you go in that order, you'll be good, okay? So, one more topic that we need to go over in this chapter, that's the idea of relative velocity. Relative velocity. Velocity is always measured within a reference frame. Okay, so when you say the car is going with 60 miles per hour, even if you don't mention, actually, we understand that you're talking about the velocity with respect to the road, right? But imagine 2 cars on the highway. One is going with 60, the other one 70 miles per hour. I mean, 70 miles per hour is fast, but as that guy passes you, in your reference frame, looking from the window, okay, it appears as 10 miles per hour. You just subtract 60 from 70, you get 10, right? I mean, that's something very intuitive, right? So, this is the concept of additional velocities, okay? And velocities are vectors, so 2 or 3 dimensional problems that involve relative velocities will require adding vectors. If you do it systematically, you'll never make a mistake, okay? So let's fix notation, for instance. Let's start with 1 dimension. I'm going to generalize to 2 dimensions after that. So let's say you have a car or a train, let's say a train, and then the train is, this is the car on the tracks. This is train. And then you're bored, you just want to play ball with your friend, and you throw a baseball in this direction, okay? So this is ball. Now, when you say the speed of the ball, okay, 15 meters per second, are you talking about the speed of the ball with respect to the train, or with respect to the tracks, or with respect to a plane that is flying, okay? You can come up with a million different velocities, so you got to be careful. So let's call it v, but let's use indices. B, let it be ball, okay, VB, with respect to the train. The train, well, T. Okay, so, well, tracks start with T as well, so let's say ground, same thing. Okay, there's a train station, so G. So VBT is the speed or the velocity of the ball with respect to the train, and then you have the speed of the train. I keep saying speed, but what I actually mean is velocity. And you have the velocity of the train with respect to the ground, VTG. Okay? So, if I add these two, what will happen? This is 15. If that's also 15, 15 plus 15, I will get 30 miles per hour. That makes sense, right? I mean, you can't throw the ball maybe 30 miles per hour. You're not that strong, but if you use the train will help you, so you will get that speed. So what happens here is, you get rid of the index here, T, which stands for train. What does remain? B and G, right? So you get V, B, G, which means the velocity of the ball with respect to the ground. Okay? So if you follow this convention, let's put the arrows on top. If you follow this naming convention, you know, you'll always find the answer without hassle, all right? Because you may have 5 velocities to add. Just get rid of the indices in this manner. This is called contraction, actually. Contraction. Okay, the train disappears in your equation and you end up with the final velocity with respect to the ground. What if you are in 2 dimensions? Okay, this could be a plane. All right. Now, a plane may have a velocity with respect to air, right? But if the air is also moving, which means wind, right? What are you going to do? You have the velocity of the plane with respect to air, but there's also wind. The velocity of air with respect to ground or airport, you know. Same thing, you contract A and you get the velocity of the plane with respect to ground. You want to go from Houston to Dallas, it's in the north, but there's a strong wind, and if you may end up in Fort Worth or something, right? So when you add these 2 vectors, you may end up with the velocity vector, which will take you to your destination, or a boat in a river. Same thing, the river flow, right? So it applies in many cases, and it's a convention, matter of convention. I mean, use the first index as the index representing the object, the second index after comma. You don't even have to put the comma, but the second index represents the frame of reference. If you line up them like this, you will get the answer easily. Okay, so that's the idea of relative velocity. So let's just solve problems. Okay, this is the that's pretty much what's in the book. Make sure you watch that video, Vectors Part 1. Otherwise, none of this will make any sense. All right. Let me check if the recording is okay. It's going on. Great. So let's solve problems. Okay. I'm gonna clear canvas and find some problems from the book. The first section is about position and displacement. Let's solve number 11. 11. Okay, I guess I need more light here. Give me a second. Okay, more light, better. You will be hiking to a lake with some of your friends by following the trails indicated on a map at the trailhead. The map says that you will travel 1.6 miles directly north. So let me write it down. 1.6 miles north, N stands for north. Then 2.2 miles in a direction 35 degrees east of north. Then finally 1.1 miles in a direction 15 degrees. What is that? North of east. Okay? So it has 3 parts. At the end of this hike, how far will you be from where you started? And what direction will you be from your starting point? How far means find the magnitude of the displacement vector. Find the direction means, well, is it northeast, northeast, whatever. Okay, we're going to find the direction in angles. Now, we don't have to use the graphical method. The component method works fine, but I'm going to sketch it anyways, okay? So this is what it looks like. The first displacement is just north. By the way, north, let's pick north as up in this paper or blackboard. South down, east is right, and west is left. Okay? So my picture is based on that. So here's the first vector. Oops, okay, let me just start over. Okay. Let's give it a name. A1. North. And the next part is 35 degrees east of north. So I'm going to call it A2. But A2 makes an angle of 35 degrees with the vertical, which represents north. Okay? And then 15 degrees north of east. So this is the eastward direction, east-west direction. 15 degrees north of that. Like that. So that is A3. A3, and that is 15 degrees. Okay? So where do I end up? I end up over here. Means this is my displacement vector. Call it D. And that will be the sum, right? I mean, follow the tail to tip rule. This will give you the displacement. A1 plus A2 plus A3. Okay, so once you write it like this, the rest is just the component method. You need to write this equation, this vector equation, in its east-west and north-south directions. Okay, I'm not going to call it x and y. You can if you like. I mean, you can call west-east as x and south-north as y, and then you can write dx and then dy. Okay, no problem there. Or you can just call it the east-west direction, and you can call you can write the equation and then do it the north-south. I'll leave that to you. Okay, both are okay. So let's do the east-west direction first, and then write down the component that corresponds to that change. Okay, so the three vectors are added, but the first one, A1, does not have any east-west component because it's lined up in the north direction. So you will have nothing that will come from A1. Put a 0 there. What about A2? Does it have a component along the east-west direction, which you would call A2x if you call it x? Yes, there is one, right? That is actually, if you consider the right triangle that is formed by hypotenuse, which is A2, and then these two lines here, you can easily see that its component along the east-west direction is A2's magnitude times sine 35. So we have there A2 magnitude, that is 2.2 times sine 35. Okay, so if that's not too obvious for you, you can always draw your box around it, like we did in the previous chapter, and then realize that this is the east-west component and this is the north-south component, and the east-west component, this side is equal to that side because we're talking about a rectangle here, and this is the 35 degrees. Now sine of 35 is side opposite divided by hypotenuse, therefore side opposite is hypotenuse times sine 35. Okay, that's why I wrote here 2.2 times sine 35. And then A3 will have a component in the east-west direction also. This time I need the cosine of 15 because that's the angle it makes with the horizontal dashed line, right? So I need the magnitude of A3, which is 1.1. Just multiply it by what? Cosine 15 degrees. So find this, and that will be the east-west component of the displacement vector d. So 2.2 sine 35. Make sure your calculator is set to degrees, not radians. Plus 1.1 cosine 15. Okay, 2.32, 2.3. Let's keep one more digit, 2.32 miles. That's the east-west component of the displacement. What about the south-north component? Now A1 does have contribution there, right? Itself, 1.6 actually. That's the component along the vertical or north direction. What about A2? That is 2.2 cosine 35, right? This one, this side here, cosine 35. And then A3 will contribute 1.1 times sine 15. All right, so 1.6 plus 2.2 cosine, what, 35, plus 1.1 sine 15. Okay, this is 3.686, let's say 3.69. miles, but I want to know what the length of D is actually. The magnitude, right? The magnitude of D, this distance from this point, beginning to end, I have to apply that hypotenuse or Pythagorean formula again. So 2.32 squared plus 3.69 squared. 2.32 squared plus 3.69 squared, and take the square root of that. 4.35. I'm going to round it to 4.4 miles. Okay. So this vector D here had two components. The x component was 2.32. The y component was 3.69, or south-north instead of y. Okay, good. What about the angle, the direction? Let's find this angle here, phi. Phi would be arctangent 3.69 divided by 2.32. So 3.69 divided by 2.32. Take the arctangent. 57.8 degrees north of east. Okay, and that will be the direction. So chapter 3, problem number 11, 4.4 miles at 58 north of east. Okay, good. This was a displacement problem. Let's do velocity. Okay. Let's do an average velocity, 19. An average velocity problem. Jason drives due west with a speed of 35 miles per hour. For 30 minutes. Okay, this is west. And then continues in the same direction west with a speed of 60 miles. So still west, 60 miles per hour for 2 hours. All right. And then drives farther west. Okay, same direction again. 25. It looks like it's one-dimensional motion. 25 miles per hour for 10 minutes. Okay, so what is Jason's average velocity? Okay, my cat wants to come in again. It's so cold outside, I don't know what he's doing outside. Okay, so what is the average velocity? Remember, average velocity is displacement delta r. In this case, I can just call it x. Delta x over delta t. Alright, so here's what you should not do. Okay? If you take these numbers and find the average of them, you add them and divide by 3, for instance, that will be completely wrong, okay? That doesn't apply. Just use the definition. Average velocity is defined as delta x over delta t. So, what are the delta x values though? Okay, that's what we have to find. So, in the first interval, there are 3 intervals. 35 miles per hour, 60 miles per hour, and the 25 miles per hour are the velocities in those intervals. And we know for how long does he go with that speed. So we can find the displacement in each interval. Okay, let's find that. So, in the first interval, it is 30 minutes, which is half an hour, right? So t is 0.5 hours. So if I multiply 35 miles per hour by that time, which is 0.5 hours, I will get what? I will get the distance. That's 17.5 miles. And then I do it for the second interval. Now I have 60. Okay, 60. My cat is messing with the camera. Okay, let me make sure I'm in. Okay, right there. 60 miles per hour. 60 miles per hour for 2 hours. That makes 120 miles. Okay? And then in the third phase, just 10 minutes. Okay, so 25 miles per hour. Now, how many minutes are there in 1 hour? 60, right? So 1 hour has 60 minutes. And then for how long? 10 minutes. Okay, so let's move that a little bit here. All right, so the answer will be in miles. Just divide 250 by 60, or 25 by 6. That is 4.17 miles. Okay, so the net displacement then is the sum of these numbers. 17.5 plus 120 plus 4.17. That is 141.67 miles. All right. What about time? Let's write the time in hours. So we have 0.5 from the first segment plus 2 from the second segment, and 10 minutes is 1/6 of an hour, 1/6. Okay, so this is the total time. So let's do the math now. Let's divide this number by 2.5 plus 1/6, and that gives me 53.13. Well, just 53, let's say 53 miles per hour. Okay, so that's obviously not 35 plus 60 plus 25 divided by 3. Okay, never do that. Okay, so that is the average velocity. Let's check this number before we move on. It also says sketch a motion diagram at 10-minute intervals. Okay, I'm going to worry about that later. Let's confirm the answer first. Okay, chapter 3, 19, 53 miles per hour. 53.1, I guess what I said, 53.1 miles per hour. Okay, so I'm going to put a bookmark here so I can come back. Alright, so sketch a motion diagram at 10-minute intervals. Okay, so let's try to draw this motion diagram. This is west, and the car is moving to the right in this picture. I'm going to show the car as a dot, alright? I don't need to draw many dots, because many cars. How many do I need? It says 10-minute intervals. So I have half an hour, 2 hours, and 10 minutes. So I will have 3 plus 2 hours means 12, right? 12. And then 1. I'm going to have 14 dots. I'm sorry, 13, 16 dots. Okay, that's what 10-minute interval means. Okay, so in the first phase, I have a speed of 35, and then 60, and then 25. So this will not be to scale. Let's mark these points. This is 17. Okay, maybe shorter than this, huh? 17.5 miles. And then there is this segment of 120 miles. And then finally 4.17 miles. Alright? Now the first 3. Okay, so I have 3 intervals. I have to be careful here. So this is times 0. Alright, so it's constant speed, so I can use equal intervals. But I will have 30 minutes. So this is after 10 minutes, this is after 20 minutes, this is after 30 minutes. And these are all equally spaced, okay? All equally spaced. So now T is 30 minutes. And then I have, for 2 hours, I'm going to almost double the speed. So I need larger intervals. Okay, I'm not going to draw all these 12 points. I don't have room, but I'm just going to put dots here. You know what's going to happen. So by the time I reach here, it'll be 2.5 hours. 2.5 hours. And then I reduce the speed to 25. Okay, so every 10 minutes. So actually it's gonna be even smaller like this. So let's make sure this reflects that. Okay. So that is what, 4.17 miles. So imagine this interval is smaller than even those. Okay, so it's not to scale, but you get the idea. Alright? Okay, this was 19. Let's do a problem. Okay, this was average velocity. Do we have an instantaneous velocity problem, right? Let's see. All right. Okay, there are a couple of problems here with pictures and I don't know, let's start with 23, I guess. 23. It says speedometer readings are obtained and graphed as a car skids to a stop along a straight line path. Okay, so we're basically talking about slowing down, alright? So I'm just going to draw that. I'm going to try to draw that. And this will be the time axis, of course. And this will be the velocity in the x direction in meters per seconds. So time goes from 0 to 16. All right. The first 4 seconds the velocity doesn't change in 4 seconds. That's 20. Okay, my cat is messing with the camera again. All right, 20. And then between 4 and 12, okay, so you hit the brakes and the car starts slowing down. So it slows down to 0, okay, a steady decrease in velocity, a straight line, okay, down to 12. And after 12, I see a horizontal line here. What does it mean? It means the velocity is 0, okay? I mean, the car is not in motion at all. Velocity 0 means it stopped, okay? But time keeps running, so that's why it's included in the picture. Okay, so that's the picture here. Going back to the problem, how far does the car move? How far does the car move between t0 and t16 seconds? Delta x is what? Between 0 and 16 seconds. Well, nothing happens between 12 and 16 seconds anyways. So the question is, what is the displacement between 0 and 12 seconds, right? So what do we do? Remember the area under velocity time graph gives us the displacement. Find the area. Now, this looks like a trapezoid, okay? But a trapezoid is nothing but a rectangle attached to a triangle, right? So think of it as made of 2 parts. The first part is a rectangle on the left, and then you have a triangle on the right. So you can find the area. You don't have to memorize the formula for a trapezoid, which is not that hard anyways, but you can just use this method and find the area. So the area of the rectangle is 4 times 20. Alright? And now add this, the area of the triangle. Now the formula is 1/2 times base times height. Base is 12 minus 4. We multiply that by the height, which is 20. Okay? So this area will give you the displacement. So this gives you 80 meters plus, okay, this is 10 times 8, 80. Okay, so 80 plus 80, 160. 160 meters. Now, if you don't want to do it like this, since there's a picture and in the picture you have squares, you can count the squares. That's also okay, all right? But then you have to know what one square corresponds to in meters. So either way, you end up with a number which is 160 meters. Okay, that's number 23. And then what else? Sketch a motion diagram. Okay, motion diagram again. Sketch a motion diagram showing the position of the car at 2-second intervals and sketch a graph. Sketch a graph of x as a function of t. Okay, so let's start with the sketching the graph and then the motion diagram. So I'm going to try to sketch the x here, right below the velocity. So that's time, that is x. Now remember what I said about the position? I can only know the displacement, but unless I know the original location or the initial location, I can't know the final. So there are possibilities here, okay? So I can always start from the origin, you know, there's no harm in that, but it's not the unique answer. That's what I'm trying to say. So let's see what happens here. For 4 seconds, it moves with constant velocity. So what happens to x? Well, x keeps increasing, right? But how? That's what we want to find. Now, I'm just going to draw a line that follows here number 4. So the times match. Okay, this is 4 seconds here. Now x has to increase in a steady manner. Why? Because I know that the slope of the xt plot gives me v, right? So the instantaneous velocity can be found by drawing a tangent to the position time graph at any given point and finding the slope of that tangent. And along any point here, tangent is this line because it's just a straight line. So I have a constant slope. Constant slope means constant velocity. Okay, that's why it's a straight line. But see what happens after that. After 4 seconds, my velocity goes down, which means the slope of this tangent should also decrease all the way to 0 actually. So by the time t shows 12 seconds, actually, the slope should be 0 right over here. So how do I join these 2 points here? This one and that one. It cannot be a straight line anymore. Okay? It's going to be a curve because I know that along a curve the slope changes. Okay? So my slope has to start at 20. So starting point has to be matching the original line here, meaning the original slope, but the final slope has to be 0 over here. So how can I match those 2 points? Simple, like this. Okay, I mean the drawing is not very good, but you can see what's happening. Here is the slope, which is 20. Here's the slope, final slope, which is 0. Okay, 0 slope. The velocity was decreasing between 4 and 12 seconds. Although it was decreasing, x kept going up, right? I mean, it's not like you're hitting a brick wall and then you stop all of a sudden. No, you slow down, the x values keep increasing. But then you finally come to a stop, which happens at 12 seconds. That's when x no longer increases. So after that, x remains the same. Right? But I said this is not the unique way. I mean, I picked the origin, which means x equals 0, as my starting point. Maybe you would like to pick a negative x value. You can, okay? There's no harm in picking a different one. So this will be the alternative. I'm going to use a different color. Let's say blue. Let's say you start from here, and then you want to go, as long as you're parallel to the first picture that I drew, you're in good shape. So it could be something like this. That's possible. Or you can start with a positive x, and you can go up. And then, okay, and you can shift it any way you like. These are equally fine. Because we're not told, if I read the problem correctly, we're not told where the car was when t was 0. That's pretty much it, okay? So we don't know it. That's why you have this freedom of locating it vertically in any position. Okay, that's the graph. What about the motion diagram? It says 2-second intervals. Okay, so let's try 2-second intervals on a motion diagram. This line now represents the x. Okay, and the car. Okay, let me do this. 2 seconds. The total is 16. Okay, so in the beginning we have 20 meters per second. So the maximum speed means the points will be separated. Okay, so I will have one, which stands for t equals 0, another one here, another one over there, 3 points. Okay, so this is t equals 0, this is t equals 2 seconds, and this is t equals 4 seconds. But then between 4 and 12 it's going to slow down, okay, gradually. So I need to make those spacings smaller and smaller. Okay, I'm going to try to do it now. So the next one will be here, next one will be here, next one will be here, next will be here, next will be here. Okay, I'm trying to make them closer to each other. Closer. How many? Okay, so 6, 8, 10, 12. Okay, I'm done actually. 12. This is t equals 12. This one here. And after that, we're not even moving at all, so I can just get rid of those. Okay? So, that's the motion diagram. If I were to draw this with the 1 second intervals, okay, let's try that. Let's add one more point in between. Now between 0 and 2, the midpoint here, that's t equals 1. And between 2 and 4, the midpoint, that's fine, 3. But again, after 4 seconds, my points cannot be exactly in the middle. They should be a little bit to the right. Okay, so I need to pick this here, and then this over there. Actually, you know what? Hang on. It's kind of hard to draw now, but something like this, okay? So it's got to get smaller and smaller. Okay, so this cat wants to go out again. Give me a second. Okay, so this was 23. Let's do another one. Okay. Velocity. Let's do this one, number 28. 28. Okay, a graph is plotted of the vertical. Are we recording? Yes. A graph is plotted of the vertical velocity component of an elevator versus time. Okay, so an elevator is actually one-dimensional motion, either up or down, right? The y-axis points up, it says. So we're talking about Vy here. Vy. And of course we have the horizontal axis as time. So it starts from 0, increases steadily, and then reaches a maximum, and then goes back to 0, and then remains there. No motion at all here, velocity is 0, and then comes downward. Now it's moving downward, right? Velocities are negative here, and slows down, goes back to 0. Okay, let me mark the numbers here. This is what? 1, 2, 3, 4, 2. 2 seconds here. Time in seconds. And this is 8. 8. This is 10. 12. 14. All right. 16. 16, 18, 20. All right, and this is 2 meters per second. And this is -2 meters per second. Okay, so the elevator starts from rest, all right? Let's say a certain floor starts from rest, but then the velocity is positive and up is positive. That's what they say. So up is positive. Therefore, we know that the elevator is speeding up for 2 seconds. So here, speed up. Reach a maximum speed, which is 2 meters per second, and maintain that speed. So this is constant speed here. Constant speed or constant velocity, right? And then slow down. All right, so it's sped up. Maintain the speed for 6 seconds, and then another 2 seconds for slowing down. It stopped at 10 equals 10 seconds. So no movement here. No motion. Okay, it's at rest. After 14 seconds though, it's speeding up again, all right? But in what direction? In the negative direction. So here, speed up in the negative direction, which means downward. Okay, it's coming back and reaches its maximum speed. Which is downward, maximum velocity is downward, and then it slows down while still moving in the negative x direction, negative y direction. Slow down. Okay? But remember, it's slowing down but still moving in the negative y direction. And then stops at 20 seconds. Alright? That's how you interpret these segments in a velocity time graph. So, A. How high is the elevator above the starting point, which is t equals 0, after 20 seconds have elapsed? What is delta y, in other words? Alright? So how high is the elevator? Find delta y in terms of meters. How do you do it? Simply find the displacements. So in the first 10 seconds, let's say, from t equals 0 to t equals 10 seconds, the area here gives you delta y, okay? So remember, you are going up in that interval, right? So in this interval, just simplifying the area. So we have two triangles and a rectangle here. So the area, which is delta y, I'm going to call it delta y 1, because there's also a going down part, right? So delta y1 will be the first triangle, 1/2 times base, 2 times height, 2. This one. And then I have the rectangular part, that is 8 minus 2 is 6, right? Plus 6 times height, that is 2, plus this triangle, that is 1/2 times base, which is 2, times height. Alright, 2. So 2 plus 2, 4, plus 12, right? 2 plus 12, 14 plus 2, 16. What? Meters. Alright, so that's 60 meters above. Now, between 10 and 14, there's no motion. What about between 14 and 20? So from 14 seconds to t equals 20 seconds. Let's call it the second part, delta y2. Now remember, it's going downward, okay? So I'm going to find the area, but it'll be a negative number. It'll be a negative number. Let's put a negative here. It's moving downward. Okay, again, I have a triangle here. 2 times 2 divided by 2, 2. 16 to 18, 2. 2 times 2, 4. Plus 18 to 20, 2 seconds. 2 times 2 divided by 2, 2. So 2 plus 4, 6 plus 2, 8. This is negative 8 meters. So what is the net displacement? I just add these. Delta y is delta y1 plus delta y2, that is 16 plus negative 8 meters. Alright, so that's part A. 8 meters above the starting point. Alright, what is B? When is the elevator at its highest location above the starting point? When? Okay, please do not say, oh, I'm looking at the graph, it looks like 8. No, between 8 and 10 seconds it's still moving, right? So, here, right there, between 10 and 14 seconds, that's where it is at the highest position. Describe the motion in words. I just did that. Sketch a graph of y, meaning the y coordinate, as a function of time. Let's do that. So I'm going to try to do it right above it, actually. I'm just going to extend this here and call it y, and then this will be the time axis. I'm just going to try to match the times. So this will be the 2 seconds. This will be the 8 seconds. This will be the 10 seconds. 14. 16. 18. And 20. Okay, so let's do this. Let's take the initial y to be 0. Again, same thing. Remember, I mean, there's a freedom of picking your initial y. This could be the 10th floor, 100th floor, or the basement. You know, it's up to you. I'm going to pick y equals 0. But I know that in the first phase, it goes up 16 meters. Okay, I have to reflect that, and I know that it's going to come back 8 meters downward, so it's going to end up at 18. So I know I need those numbers here. So this is 16 in meters, and I also have 8. Okay, so where do I reach 16 meters when t is equal to 10? So when t is equal to 10, I have to be right there. All right? And I have to stay there until t equals 14, which is here. So between 10 and 14, it has to be a straight line. Okay. So what about in between, right? So remember, between 2 and 8 seconds, the speed doesn't change, constant speed. Constant means straight lines, constant slopes in the position graph. But in the other two, in the first 2 seconds and the last 2 seconds in that 10-second interval, I cannot have a constant slope, all right? Actually, the slope has to increase for the first 2 seconds, and the slope has to decrease for the last 2 seconds. I have to keep that in mind, okay? So, it has to start from 0 velocity, I also know that, right? It has to start from 0 velocity, which means the slope has to be 0. 0 slope means horizontal line. So I have to start from 0, but then quickly increase my speed. So I'm gonna pick something like this. Okay? A gradual increase in y, but between 2 and 8 seconds, I have to maintain that slope. Alright? So again, maybe I should use a thicker pen here. This has to increase gradually, but after that, it has to remain constant. In the last 2 seconds, the slope has to go back to 0. So it has to be like this. Okay, so here I have this shape if I exaggerate, and over here I have that shape. Okay? Now what happens after 14 seconds? It has to start from 0 speed, because the slope is 0 right there. But it has to increase its speed in the downward direction. The velocity has to be negative until it reaches a maximum velocity of -2. So same thing will happen, but in the other direction, meaning it's going to speed up, reach a maximum speed, and then slow down like that, because I know that I have to be at 8 meters above. This is where I need to be. when t is 20. Okay? So make sure when t is 20, the slope here is exactly 0. Over here, you have 0 slope. Like you had it also here, that's also 0 slope. This is the maximum slope in the negative direction. This is the maximum slope in the positive direction. Okay? So that is a sketch of the y versus t plot. Okay, now let's move on to acceleration. Acceleration, and let's do 41. There's a graph there. Let's do 41. How are we doing on time, by the way? It's been 1 hour and 25 minutes. Okay, so after this example, I'm going to stop and maybe make another video for other applications of Newton's laws. Let's just do 41 now and stop after that. The graph shows Vx versus t for an object moving along the x-axis. Let's draw it. T, and then there is Vx. The motion is along the x direction. Velocity given in meters per second and time in seconds. And it looks like for the first 5 seconds, the speed doesn't change. So the velocity is 20 meters per second. And between 5 and 9, there's a steady increase in the velocity up to 40 meters per second. And between 9 and 13 seconds, there is a slowing down, a deceleration, if you will. Slowing down and stops. At 13 seconds, it stops and remains at rest for another second. That's our data, all right? So, maintain the speed for 5 seconds, increase the speed, and then decrease the speed. Constant velocity, increasing velocity, decreasing velocity, all the way down to 0. That's how you read that graph, okay? So, A. What is AX? AX means instantaneous acceleration at t equals 11 seconds. Okay? See, that is picked for a reason. If they said, what is the instantaneous acceleration at t equals 5 seconds, or t equals 9 seconds, or t equals 13 seconds, that problem will be wrong from the start, okay? Why is that? Because how are you going to find the slope at a joint or a corner like this? Okay? I mean, in real life, you will never have corners like this. What you really have is actually some smoothed out, okay? Nature likes to do things gradually. But this picture has straight edges, corners. That's why they do not give you those time, but instead they give you a time in between, right? So 11 is, where is 11? 11 is somewhere here, between 9 and 13. And that's okay, because you can find the slope right here when t is 11, okay? Just draw the tangent, which is the line itself here, and find the slope of this dashed line. That is, by definition, the acceleration. It's a negative slope, right? It's going to be a negative number, but that's what we were expecting. I mean, positive velocity versus negative acceleration means slowing down. Anyway, so we just find the slope. The slope will be, okay, you can use a rise over run idea. So you go by negative 40, 0 minus 40, in a interval of 4 seconds. 13 minus 9 is 4, right? So basically negative 10 meters per second square. That is your acceleration. Part B, what is the acceleration, AX, at t equals 3? Again, they just give you a nice number here, which is not at the corner here, right over there. You just need to find the slope. Okay, you don't need any calculation. The slope is 0. So AX at t equals what? 3 seconds is 0. Horizontal line. There's no acceleration in that interval. I mean, they could have, say, 1 or 2 seconds as well. No, it doesn't matter. C. Sketch a graph of a x of t. Sketch a graph. Okay, I'm just gonna squeeze it here. But I want to align it. Okay, so 5 seconds is here, 9 seconds is here, 13 is here, 14 is here. So between 0 and 5, there's no acceleration. Okay, slope is 0. So let me use bold again here. All right. But what about after 5? Now between 5 and 9, the velocity increases in the positive direction, right? So I have a positive acceleration there. What is the value of that acceleration? I have to find that slope. If I want to put that number over here, I have to consider this, which is a 20 over 4, right? 5. That's 5 meters per second square. And then I already calculated what happens after that. That's negative 10, right? So right here. That's negative 10 meters per second square. So that is the sketch. So what happens at these 2 points here? I mean, you can just combine them if you like, or you don't. You just leave it like this, doesn't matter. But again, in nature, you don't have these sharp edges, okay? What really happens is a very turn. I mean, what happens is this. Okay, so that's what happens really. Otherwise, you can't calculate the slopes. All right, so that's the sketch. The final part. How far does the object travel from 12 seconds to 14 seconds? How far does the object travel from 12 to 14 seconds? Where is 12? 12 is right there. Okay? And this little area here, that's what you need to find, okay? So, if you look carefully in the picture, that point corresponds to 10, alright? So that little area here, remember between 13 and 14 it's not moving at all. So whatever happens between 12 and 13, that's what we're after. Just find the area of that, triangle, okay? So 1/2 times base, which is 1, times height, which is 10, 5 meters. Okay, 5 meters. So 5 meters in the positive direction or negative direction? How do we know? The direction of the displacement always is found from the sign of the velocity, okay? So please don't make this mistake, okay? Just because the slope is negative there, don't think it's going backwards or anything. No, the motion is always forward. It's just slowing down, that's all. Okay, so it's still 5 meters, but slowing down. Alright? So between 0 and 12 or 13 seconds, velocity is never negative. If the velocity were ever negative, that's when you would say, oh, it's moving in the negative direction. No, it's not moving in the negative direction. It's all positive. Okay, let's check the answers really quick, and then I'm going to stop there. 41. A is negative 10, B is 0, C is just like I drew, and then 5 meters is D. Okay, I mean there's more to do in this chapter, but I'm going to take a break now and stop the video. It's been an hour and 35 minutes. That's good. Until next time, goodbye.